Just a few final adjustments. Should be ready for launch. Looking good. Great. Another scientific investigation. What's going on out there?
Stella, have a look at this. It's really strange.
You put the balloon in the bottle. And we blow it up. It just doesn't blow up. Let me have a go. There's something in the bottle stopping it.
But it's empty.
Maybe there's no room for it. There's room for it to blow up a little bit, but it won't blow up at all.
We need science in action to investigate. It's really strange.
Yeah, see what you mean. Must be something in the bottle that's stopping it. Can't see anything in there. Is there anything there? When you blow up a balloon, you're simply filling it with air. But of course there's air outside the balloon too. I mean, you don't see it, you don't smell it, you usually don't feel it. But air is a mixture of gases and behaves like any gas. So, if you cool it enough, it should turn into a liquid. Well, this should be cold enough to do it. But first, let's see just how cold it is. This bucket contains liquid nitrogen. It's much, much colder than the North Pole, minus 190 degrees Celsius. So cold that in just a few seconds, my ice pop becomes a frozen lolly. So, back to my balloon full of air. Okay, well, watch this. The air's become a liquid. It's condensed. But all that air has become just a few tiny drops of liquid air. And as it warms up in the room, it turns back into a gas. What exactly is going on here? Imagine you had an eye more powerful than the most powerful microscope. You would see a liquid is made out of many tiny particles jostling for space in the container. When you heat the liquid, the particles jostle more and more. The particles get so excited and so energetic that more and more can escape from the liquid. They become a gas. Once they've escaped from the liquid, the particles spread out. They take up much more space than the poor old particles still squashed in the liquid. Air as a gas, air as a liquid. As the liquid air warms up in the room, just watch it push out the wall of the balloon. The air particles are spreading out and pushing against the inside of the balloon. But remember, there's air outside the balloons too. And there's air inside this bottle. Could the air in the bottle be pushing against the outside of the balloon? It's time for Trish to take up this investigation.
Now, this investigation is going to start with a bit of a party. But it's a themed party because all of these things have got one thing in common. They all contain air. There's air inside the balloons and outside them too. There's air in this and this. Air in these crisp packets and lots of air inside this squirty cream. But this is no ordinary party venue. In fact, it's not a room at all. It's a chamber that can be completely sealed. This is a decompression chamber. The seals are all airtight, so you can actually control the amount of air inside the chamber. You can add or remove it through special valves. Help! Help! Oh, at last! Oh, thanks a lot, Shelley. Sorry about that. That is certainly not the place to be. Anyway, I forgive you. Come on, it's time for the experiment. It's time to add the air. As the air is added to the chamber, it gets more and more squashed, so it pushes harder and harder against the outside of the objects. The air pushes against the outside of the crisp packet. And it squashes the whipped cream. Right, and as if our party hasn't suffered enough, it's time to see what happens when we do the reverse. Take it away, Shelley. The air, that is. Now the air is being removed from the chamber through the valves. And look what's happening to our experiments. This time the balloons are getting bigger. There's less air in the chamber, so it's not pushing as hard as the air inside the banana. The air in the mousse expands, so does the air in the freshly whipped cream. The exploding's finished. Oh my goodness. Well, this certainly goes to prove that air does push. And if it can do this to our big banana, imagine what it could do to us.
Yeah, no way would get me in there.
Yeah, you'd explode.
Or get squashed.
Imagine all the air pushing at you, squashing you.
Yes, but there's air all around us, isn't there?
Yes.
And it pushes all the time?
Yeah. Yeah.
So why can't you feel it pushing you now?
Smart question. You can't feel it because air always presses equally in all directions. It's called air pressure. Even though you can't feel it, ordinary air pressure is very powerful. Watch this. This may look like an ordinary bottle, but it's got holes in the bottom. But when the top is sealed, the air outside pushing up holds the water inside. As the candle burns, it uses up oxygen in the air. The egg seals the top, so no more air can get in. Soon, the candle uses up all the oxygen in the air. There's more air outside the bottle than inside, so it pushes the egg into the bottle. But pressure differences caused by burning can have much more serious effects.
What a singe. OK, I own up, it wasn't me. It was our Betty here, who fortunately has a plastic head. Thanks, Betty. But that was caused by a change in air pressure. I'm meeting firefighter Trevor Norwood to find out how.
Hi, Tricia.
This house is to be our first casualty.
Here we are, Trish.
Oh.
Time for a controlled demonstration.
Oh, is this safe?
You're in safe hands today, but of course playing with matches can be very dangerous.
This small-scale simulator shows what happens when a room catches fire. The fire soon takes hold. Woo! It's really starting to get going now, hasn't it?
As you can see, it's using up all the oxygen in the room, producing lots of smoke, lots of hot gases, and the fire's going extremely well.
Is this like a real house fire?
Well, there's something that's not quite right about this model. What do you think it is?
It's got no front.
That's right. On a real house, obviously, you would have closely fitting doors and windows to keep the heat in, and you wouldn't have such a good supply of oxygen going into the rooms.
Right. So time for something a bit more realistic. Very comfy. But this is actually a large-scale training rig built by the Essex Fire Brigade to train their firefighters. I think things are about to hot up. Time to leave. Although it might not look much like a house outside, this unit is very realistic. The fire burns freely with an ample supply of oxygen coming in through the door, until Trevor closes the doors and windows. No more air can get in, and the fire inside uses up the oxygen and starts to die down. There's now less air inside the unit than outside. Right, I think we're just about set. Are you ready, Betty? When Trevor opens the door, the smoke billows out, but the air flows in. Let's look at it again. The air outside at higher pressure rushes in. The hot gases ignite and explode. A flashover. Understanding the science means firefighters now know how to tackle such fires safely.
This'll cool me off. Now, if I ask you what's making the drink go up the straw, I bet I know what you'll say. Go on, say it. Well, I won't use that word. You know why? Because it's not me that's making the drink go up the straw. It's air pressure. And without air pressure, however hard I S-U-C-K, the drink won't make it up the straw. Watch. This is a sealed container. No air can get in at all. You need air to push down on the surface of the drink to push the drink up the straw. By sucking, all I'm doing is removing the air from the top of the straw. But there's just not enough air in the sealed container to push the juice all the way up the straw. There is no such thing as a sucking force. And if you still don't believe me, watch this.
Yes, I'm tackling a fire again, and it looks pretty fierce. But this time, air pressure is going to help me put it out. I hope. Don't worry, I'm in the capable hands of the London Fire Brigade Training Centre. Right, we've got our container full of coloured water with 2 hoses dipped into it. The first hose goes up to the lower balcony where Kevin is standing by. Hi, Kevin.
Hello, Trish.
Our second hose goes all the way up to the higher balcony where Roger is standing by. Hi, Rog!
Hi!
Who do you think is going to be able to put out the fire first? Is it Roger or will it be Kevin? Well, the first thing they've got to do is get the water up the hose using air pressure. Just like when you're drinking with a straw, we need to remove the air from the top of the hosing using a pump. The air pressure pushes down on the surface of the water to send the water up the hose. Anyway, the fire's really starting to get going now. So you ready, guys? On your mark. Get set, go! And they're off. Well, Kevin's off the marks first, but Roger's close behind. Yes, it's neck and neck as the pumps remove the air from the top of the hosing and air pressure pushes the water up the hoses. But Roger, he seems to be having a bit of trouble at the first bend. Yes, he's definitely slowing down. Oh my goodness, look at him. Oh no, he's only at 5 meters and his water seems to have ground to a halt. Roger, your water stopped. Your water stopped. Turn up the pump. The pump. Meanwhile, it's all working like clockwork for Kevin down below. Just the final stretch through the hose. Let's see how Roger's doing up top. Oh no, it looks like he's given up. And the fire's still going strong. Now the water's got to the lower pump. The pump can take over the hard work of pushing the water out of the end of the hose. Oh, well done, Kevin. Roger, what's gone on? The water seems to have been stuck in your hose.
Oh, nothing's gone wrong, really. It's just something that we have to deal with all the time, I'm afraid.
Why? What's the reason?
Well, it's one of these things where it's impossible to lift from open water to a pump at this height, I'm afraid.
What, so 7 meters is a bit too high?
It is indeed, yeah. What we're doing is using air pressure to push down the water and then push it up the hose to the pump. And at this height, you know, we're at 7 meters here. It's really impossible to get past 5.5, 6 meters, I'm afraid.
This is a problem firefighters face in real situations. When they're getting water from an open source like a river, but need to lift it higher to fight the fire, it's vital that they put the pump less than 5 meters above the water level. So you never really were in with a chance?
No, I'm afraid not.
Oh, well, never mind. Well, listen, it's my turn downstairs.
Right.
You know, when you think about it, air pressure is really amazing. Because air usually pushes equally in all directions around us, we tend to forget that it's there. But without air pressure, we couldn't get the water to go up the hose, and we couldn't even get drink to go up a straw. What's that?
Well, that's it from Science in Action. Time to get back to my rocket and finish those adjustments. But one last thing. Try this. Take a newspaper and lay it out flat on a table. Slide a ruler underneath. Now, what do you think will happen if I hit this really hard? No, you do it. It's your turn now.
It's obvious. The paper will fly up.
Here, I'll try.
It just stays there.
It's partly has something to do with the air, isn't it?
Yeah, I mean, there's air all around us, isn't there?
Yeah, and it's pushing in all directions.
Great. Another scientific investigation. What's going on out there?
Stella, have a look at this. It's really
You
strange.
put the balloon in the bottle. And we blow it up.
Just a few final adjustments. Should be ready for launch. Looking good. something in the bottle that's stopping it. Can't see anything in there. Is there anything there? When you blow up a balloon, you're simply filling it with air. But of course there's air outside the balloon too.
It just doesn't blow up. Let me have a go. There's something in the bottle stopping it.
But it's empty.
Maybe there's no room for it. There's room for it to blow up a little bit, but it won't blow up at all.
We need science in action to investigate. It's really strange.
Yeah.